Hello, everyone. Welcome to today's Snack and Learn webinar. Thank you for joining us today. Just before we start, some housekeeping items to mention. The presentation slides are available to download in the handout box on the control panel. And also, there will be time for question and answers. If you can log your questions in the question box, and we will try to address the questions at the end of the presentation. So I will hand it over to Camila and Ignacio to start the presentation. Thank you.
Okay, thank you, Sharon. Hello, everyone. We are going to present the Snack and Learn webinar of today called Evaluation of Extreme Precipitation Under Climate Change Scenarios. So, well, my name is Camila Loyola. I'm a hydraulic engineer. I've been working in WSP since the last 3 years.
I'm Ignacio Toro. I'm a hydrologist and climate change specialist. I have been working here in WSP and previously on Golder for the last 7 years. With Camila, we belong to the Chile and Argentina operation with around 1,600 professionals distributed in 4 offices in Santiago, Concepción and Puerto Montt in Chile, and one in Mendoza, Argentina. We work in the surface water team. It's based on Santiago, Chile. We are around 34 water resources specialists with a strong experience in water balances, hydrological and hydraulic models, flood assessments, and of course, climate change projections. The climate change services that we provide are usually related with hydrological studies, mainly for mining clients, but the methodologies that we apply are suitable to different industries like infrastructure, agriculture, and etc., among others. We usually assess or evaluate water balances and hydrological models with climate change. Also, the assessment of the severity of climate change on water availability through draw and aridity indices to assess the water availability to their operations. Also, the estimation of the projected change in groundwater recharge under future scenarios according to numerical models. And related with this presentation, the extreme hydrological events like probable maximum precipitation or probable maximum floods. Also, the evaluation of current and projected infrastructure response to extreme hydrological events under climate change. As you could see in the figure of the right, we assess, in this example, we assess for a mining client here in Chile, the response of the 100-year return period for a future window. We evaluate the flow depth and the flow velocity of the flow and identify some different areas of an infrastructure that is compromised. So we propose then solutions to increase the resilience and response of this infrastructure for the climate. We also have experience working in projects here in Chile, Argentina, Brazil, Peru, Colombia, and Mexico. The agenda for today is first a general context of the project, then the climate change, a brief description of the climate change database that we use, then the methodology that we use, and the results and closure and Q&A. As a general context, we assessed climate change for a mining operation in central Brazil. As you could see in the figure on the right, the mining operation is located in Goiás state in central Brazil. The client asked for the historical and future characterization of the area in terms of total precipitation, maximum precipitation, the temperature, and the evaporation, evapotranspiration, the potential evapotranspiration. Also, we have to assess the water availability projections for the operation. The selection of 3 climate change models to be used in a water balance model, which was the topic of the Snack and Learn of the last month, and the extreme precipitation projections linked or related with design and verification of infrastructure. So in the results, we will see, or we will talk about the 100-year return period, which is usually used for design and verification. Also, we will explore other return periods, but the results will be focused on that. You will see the time series of the 24-hour maximum precipitation for this area, and you will notice that there is no trend. Maybe you will expect an upward trend because we are used with the concept of an increase or expected increase in maximum precipitations due to climate change. But we have to make a difference between the observed or the historical trend, which is observed in our study area, and the expected projections given by climate change models. These are very different, and Camila will show you if there is a clear trend given by the GCMs or not. The climate change database that we use is the next GDDP CMIP6. This database is made by NASA. NASA take some climate change models and process them to give a database, a easy database to work. This data we use for this project 34 climate change models and consider 2 climate change scenarios. One moderate, the SSP 24.5, and one pessimistic, the SSP 58.5. The moderate and pessimistic category is given by the CO2 emissions, as you will see in the figure at the right. This not mean that the pessimistic scenario will show the worst, future in terms of extreme precipitation. These are different concepts that usually are confused. You will see that there are different possible futures, and inside each one of them, there are a lot of climate change models. So you could be suspecting that there is a high uncertainty in the climate change projections. Then we select these 2 climate change scenarios to limit the amount of different results that we could expect. And because we consider these 2 climate change scenarios could be a good reference of what we could expect in the future for us or for the project. The next GDDP CMIP6 database has a global coverage at a daily scale, so you will use it everywhere in the world, and the daily scale is really useful for this kind of studies where do you need at a daily scale time series. And the database is from the 1950 to the end of the century. This database has a high spatial resolution, around 28 kilometers, but this high spatial resolution is just accomplished by spatial disaggregation, so it's like an interpolation. You don't have new information when you compare with the original GCM or climate change model. This database has 4 climate change scenarios, so you could select different possible futures. We recommend that you consider almost 2 to assess the uncertainty, and have 34 climate change models for each scenario. Some scenarios have the 34 and others have less climate change models. Also has projections for precipitation, average mean and max temperature, relative humidity, wind speed, solar radiation. So you have a lot of variables to consider in your studies. And you have downscale projections, but you have to proceed with caution because these databases are corrected, are bias corrected, but to that they use global historical database. So when you compare the historical period of your climate change, of the climate change model against, I don't know, a meteorological station or the time series that is representative of your study area, they will show some differences and bias. So you will have to decide if you correct this time series again or use another approach to use this data.
Okay, so about our methodology, the first step is to prepare the data. For this, we obtain the 24-hour maximum precipitation per year for each climate change model, and then we obtain the same parameter, but for the historical record. So we have those both data sets, and the next step is to do a statistical downscaling to obtain a bias correct time series. Okay, so this process is graphed here below in these figures. In both, in gray lines are marked the climate change models, and in green lines are marked the historical records. So as you can see in the figure of the left, there is a mismatch between both datasets. And well, this problem is fixed after the statistical downscaling, as you can see in the figure of the right, where the fit is much better between both of datasets. Okay, so at this point, it is important to indicate that this methodology it can be applied anywhere, because you only need the historical records of your area of your study. Okay, so well, we have this climate change of this data, and so the next step is to do a frequency analysis. So we obtain the 24-hour maximum precipitation projection for each return period per climate change model and SSP scenario, moderate and pessimistic. Okay, so here we have our results. We analyze the future in two periods. The near future for 2031 to 2060, and the far future that we see in the next slide. Okay, so in the near future, here we present the 24-hour maximum precipitation for different return periods in both scenarios that we analyze. In gray lines are represented the projection of the climate change models. As you can see, there is a high dispersions in the results for the higher return periods. Almost or approximately the half of the projections indicate an increase in the 24-hour maximum precipitations, and the other half indicates a decrease. So the 50th percentile, the the line marked in red is around the middle and is near the historical estimation, which is the green line. Okay. So in this case, the projections are slightly higher for the moderate scenario than the pessimistic scenario respect the CO2 emissions. Only 2% of difference, but it's a tendency. Okay, so now we have the same results, but for the far future. And as you can see, the high dispersion of the projections, it's maintaining. And but in this case, the projections are higher for the pessimistic scenario, with around 30% higher than the historical estimations, and the moderate scenario project an increase around 20%, or a 20% respect the historical estimation, the the line market in green. These numbers are about the 75th percentile, which is the line marked in dark red in both figures. Okay. So now we have the question: how could you adopt a design precipitation value for the future? Because as you can remember, we talk about two periods, two different periods analysis, two scenarios, pessimistic and a moderate scenario respect the CO2 emissions. We have 34 climate change models. So there are a lot of possible future about the climate change, and we need to choose some of them. So at this point, it is important to see the data. For example, for this project, we analyze the result of this table, in which we present some of return periods for the 24-hour maximum precipitation, for this historical estimation, and for the 75th percentile projection for the moderate scenario and the pessimistic scenario. And as you can see, for the 100 return period, for the projection, for the climate change projections, the precipitations is around 200 millimeters. But these 200 millimeters with for the historical estimation corresponds to around the 1000 return period. So we thought it's reasonable to use a higher percentile. These are decisions that must be made considering the level of the risk that is willing to assume for each project. In this case, we consider that the 75th percentile was conservative enough for the projection, but it is important to mention that not always the 75th percentile it will be the response. Okay, so as closure, this methodology is adequate an adequate approach to evaluate the uncertainty of the climate change projections. With this methodology, it is possible to propose a percentile for design and verification, and again, this it will be depend about the level of the risk that is willing to assume. It is important to evaluate more than one scenario because, as we see in our result, not always the pessimistic scenario with relation to the CO2 emissions, it will be the pessimistic scenario about the precipitations, and the changes in extreme precipitation show that it's imperative to consider the effect of the climate change. So now we have time for some questions, and here are our contact details.
Thank you, Camila and Ignacio, for a fantastic presentation. Just mentioning the housekeeping items very briefly, the presentation slides are available to download in the handout box as a PDF, and also please continue to log your questions in the question box on the control panel. I will start with a question that is repeated here, just to clarify for the GCM models. Did you use daily precipitation, and then downscaled, or did you use the maximum daily precipitation and then downscaled?
I could take that question. It's a really good question, by the way. Usually, some approaches are downscale the entire time series, the daily time series, and then extract the maximum daily precipitation, and then perform the frequency analysis and have the projections for maximum precipitations. We use the other approach where we extract the maximum precipitation from the GCM models, and then we perform the bias correction, because the bias correction methods usually correct some metrics, but not all the metrics. So if you perform a daily bias correction, correct the entirely time series of precipitation, maybe you will not preserve the statistics of your maximum precipitation events. So if you want to perform directly a frequency analysis of your time series of precipitation for your GCMs, for your climate change models, I think that you need to perform the bias correction over the maximum precipitation directly, this time series, which is one value per year, is also an easy approach. It's much easier to perform a GCM downscaling with one value per year against the entirely time series of daily time series of precipitation. I think it's a better approach. You will use other approaches too. You will use climate generator, for example, and modify some statistic of your stochastic generator, for example, with some signal extracted from the climate change models. It's a different, but you could do that too.
Thank you, Ignacio, for clarifying this. I will continue to the next question. Are there any locations where climate change is manifesting itself in reduced precipitation?
I can take that. Yeah, of course. There are some places where the projection of the precipitation is to decrease. Some examples is the center of Chile, some areas of Brazil, Mexico, the north of the Africa, yeah, among others.
Thank you. I will go to the next question. What kind of biased correction approach did you use and how did you implement it?
I could take that. We usually use a univariate approach. We correct the precipitation series with the precipitation records or precipitation historical estimations. But in the last projects, we are using a multivariate approach developed by Canon. MBCN is called. But it will depend on the project or your area. For example, if you are bias correcting climate change models to water balance or hydrological model, which is based in a mixed basin, for example, or strong, which has snow and liquid precipitation, maybe you will you must to consider a multivariate approach because you need to preserve the relationship between precipitation and temperature. You will also want to use this approach if you want to preserve some correlation, some spatial correlation. For example, if you're analyzing a really big area with different meteorological stations and you want to preserve some correlation between them, you will use a multivariate approach too. We implemented in R. It's a library that Canon developed for his method. But you, my strong recommendation is that you apply some different approaches of bias correction methods and review what are the results, because we are a hydrologist. We need this time series has some meaning, some hydrologic meaning. It's not just a statistical procedure and then apply and estimate the rest of the things that we need. We need to interpret if the results have a meaning or not, and select the bias correction method based on that.
Thank you. What are the most used models for determining future climate change events?
I can take that. Well, as we saw during the presentation, there are a lot of climate change projections and possible future scenarios. So we recommend evaluate which the most recent version of the climate changes model. If evaluate if a regional climate change model is available, and of course evaluate the uncertainty. But we do not recommend select or choose one model over another without do a previous process of selections.
Thank you.
To complement that, this is because this do not guarantee that the model is correct in its projection. So you could assess or carry out some validation project or process or selection process, but this does not guarantee that this model that you select will be correct in its projection, because these are not predictions, these are projections. That's the difference.
Thank you. I will take the last question. Changes in extreme precipitation are uniform. How comparable is the trend between GCM and high resolution models?
I could take that. The projected changes over extreme precipitation are not uniform. You could see that in the results that Camila showed you. Climate change models show a high uncertainty, where some GCMs show increases while the other half project decrease. for example, in this area. In some places, we will see some agreement between climate change models, like in Peru, for example, with an expected increase, or central Chile, where the projection shows mainly a decrease of extreme precipitation and total precipitation. If you have regional models or high resolution climate change models, our recommendation is to consider them, but try to assess uncertainty and see how these high resolution projections compare against the GCMs. We have observed some important differences over the projected changes between the high resolution model and the original GCM, or the GCMs in general. So where more than the physics involved in these models, statistical or numerical issues are involved sometimes.
Fantastic. Thank you, Camila and Ignacio, for a fantastic presentation, and thank you all for all the wonderful questions that you shared with us. Apologies we didn't have time to cover all these questions, and thank you for the nice feedback as well in the comments. All the additional questions that were unanswered will be answered directly by their presenters. So thanks again for joining us today, and we will wrap up the session now. Have a wonderful day, everyone.
Bye-bye.
Okay.
Thank you.
Bye.
Thank you.